Hey everyone, and welcome. Today we are going to jump right into one of the most important experiments in all of optics, the concave mirror. We're going to see how one little curved piece of glass can play some incredible tricks with light. So, you ready? Let's get started. Yeah, you can forget all that dry textbook theory for a little while. Today we're doing it hands-on. Aaj hum mirror ka magic practically dekhenge. We're going to see for ourselves how a concave mirror can bend and shape light to create some really, really cool images. And trust me, it's way simpler than you think. All right, first things first. Section 1, setting up the experiment. You know, every great result starts with a great setup, so let's quickly run through what we need and how we're going to do it. So, what's our goal here? What are we trying to figure out? Well, it's pretty simple, actually. First, we just want to look at the image. Is it upside down, ulta? Is it bigger or smaller than the real thing? And second, we need to measure two very important distances. How far the object is from the mirror, we call that U, and how far the image is from the mirror, and we call that V. That's it. Okay, let's meet the cast for our little show. Of course, we've got the star, the concave mirror. Our object for today is just a simple candle. We need a screen to catch the image, so a piece of paper is perfect. And, of course, a meter scale to measure everything accurately. Now, how do we actually do this? It's a simple four-step process. 1. Put the mirror on its stand. 2. Put the candle at different spots, starting far away and then slowly bringing it closer. 3. For each spot, you're going to move the paper screen around until you get a super sharp, crystal clear image of the flame. And 4. Just write down your U and V distances. See? Easy. All right, the setup is done. Now for the really fun part. Let's actually see what happens as we start moving that candle around. This, my friends, is where the magic really begins. Okay, I want you to imagine the lab is all set up. The lights are a little dim, the candle is lit, and we are ready to go. Let's start making our observations. So this table here is like our virtual lab notebook. Watch what happens. When the candle is really far away, say at 80 centimeters, the image we see on the screen is small or diminished, and it's inverted, upside down. Okay, now let's bring the candle closer. As we do, the image on the screen gets bigger and bigger, but it stays inverted. But then, as we get really, really close, the image on the screen just vanishes. It's gone. So what on earth is going on here? While that disappearing image, it wasn't magic. It's just pure physics. So now we're going to move from just seeing what happened to understanding why it happened. It is time to decode the science. You see, everything we just observed in our virtual lab can be perfectly explained by 5 key situations, or cases. And I mean it. If you understand these 5 cases, you have pretty much mastered this entire topic for your exams, so you'll want to pay close attention to this part. Okay, case number 1, when the object is beyond C. Now, C is just the center of the sphere that the mirror was cut from. So when our candle is way out there, beyond C, the image gets formed between the focal point F and C. And just like we saw, it's real, it's inverted, and it's smaller or diminished. Next up, case 2, object at C. Now this one is really special. When you place the object exactly at the center of curvature, guess what? The image forms at the exact same spot, and it's the exact same size as the object. It's still real, and it's still inverted. Pretty cool, right? Okay, let's keep moving the candle closer. Now it's between F and C. What happens? Well, the image now forms beyond C. And look at that. It's enlarged. It's magnified. It's still real, it's still inverted, but it's bigger. This is basically how projectors work. Case 4, what if we put the object right on the focal point F? A very interesting thing happens. All the light rays that hit the mirror reflect back completely parallel. And since parallel lines never meet, you can't form an image on the screen. We just say the image is formed at infinity. And finally, case number 5. This is the one. This is the magic case, when the object is super close, between the mirror and the focal point F. This is why the image disappeared from our screen, because it's not on the screen anymore. It's now formed behind the mirror. And this time, it's upright or erect, it's enlarged, and we call it virtual. So, this brings us to the most important difference you absolutely have to remember. A real image is one you can actually capture on a screen. The light rays physically meet there. But a virtual image, you can't. It only appears to be behind the mirror. You can only see it by looking into the mirror itself. It's as simple as that. So let's boil it all down to one simple, powerful statement. The image you can catch on the paper screen, that's real. The image you can only see by looking into the mirror itself, that's virtual.
Okay, we've done the experiment, we've decoded the science. Now for the most important part, right? How do you take all this knowledge and use it to score full marks on your exam?
First, let's talk about what not to do. These are the common mistakes that trip students up all the time. 1. Be super careful when you take your distance readings. 2. Don't just find a blurry image. Move that screen until you find the absolute sharpest possible image. And finally, please don't forget to write down the nature of the image. Real, virtual, inverted, those details matter.
And now for the pro tips. You want to impress your examiner? Make a neat, clean, and fully labeled observation table. Always mention the nature of the image. And my biggest tip? Practice drawing the ray diagrams for all 5 cases. Practice them until you can draw them in your sleep.
So, if you forget everything else from today, just remember this one single thing. Where you put the object is everything. That one decision, the object's position, determines the image's position, its size, and its entire nature. And just think about this for a second. The exact same mirror that a dentist uses to get a magnified, virtual view of your tooth is based on the same physics that allows a massive cinema projector to throw a huge, real image onto a screen. It all just depends on where you place the object. I mean, how incredibly cool is that? And that's a wrap on our virtual lab. Seriously, if you can master this one experiment, I promise you the rest of optics is going to feel so much easier. ये experiment समझ लिया तो optics easy हो जाएगा. Thanks for joining me today, and I'll see you next time.